This video is for AP Calculus, AB Section 7.2. We're going to be looking at the disk method in this video, and then there will be a couple of the other videos, one of them with the washer method, the other one with volume by cross-section. Okay, so the disk method is one way to find the volume of a solid of revolution. Let's talk about what that means. A solid of revolution is a three-dimensional shape formed when the graph of a function is revolved around an axis of rotation. Okay, so it's often handy to look at a picture of this sort of thing. So I'm just gonna come up with a region here. I'm gonna say that I've got a region right here. We're gonna call this, or I've got a function here. We're gonna call this function f of x, and I'm gonna cut that function off over here. And so our region that we are going to be rotating, I'll try to fill this in for you, is this blue region roughly right here. So this is the region that's getting rotated around an axis of rotation. And you'll always be given an axis of rotation. In other words, you're going to be told that we're going to revolve this region around the x-axis, the y-axis, or maybe some other line. So I'm going to say that we're going to revolve this around the x-axis. So in order for this to work, in order for this really to kind of make sense, what I'm going to use is a representative rectangle. So I'm going to draw this representative rectangle in right here. We'll talk about this, or we'll review this in a second, but whenever you're using the disk method or the washer method, the representative rectangle needs to be perpendicular to the axis of rotation. So this representative rectangle will rotate around kind of like this. It's going to go back into the page and pop out of the page as well. So when we do that, what that essentially does is that forms a disk, and I'm going to try to represent that for you. I'll use a little darker color, but this representative rectangle, when it's rotated, will give us this disk-like shape. Like this. It'll go back into the page and come back out like so. So you get this nice disk, looks like a sort of a cylinder, I guess, with the axis of rotation going right through the middle of it. And if we just continue to stack these disks up, continue to make them on out here, they'll get increasingly large out there, of course. Then we'll get this three-dimensional shape. I would say that if we were going to try to visualize what the shape would look like, I'd maybe call it a bullet, with the kind of the pointy end pointing to the left there. But if you've been in class, we've worked with Play-Doh. We've also looked at a couple of demonstrations online about what these look like. So I think it's a useful thing to kind of visualize what these shapes are. We'll be finding the volume of them here in just a little bit. So just again, a reminder there, you can see at the top of the page, for the disk method, the representative rectangle will be perpendicular to the axis of rotation. So let's look at the couple of formulas that we use here to help us find the volume of these sorts of three-dimensional shapes. If we have a horizontal axis of revolution, everything will be in terms of x. So we'll use this. For a vertical axis of revolution, everything will be in terms of y, and so we will use that. We'll talk a little more detail here in a minute about why the variables have to be x's or y's depending on that axis of revolution. So let's define what we have here. Obviously, you guys know what pi is. R of x, this would be, of course, in terms of x. So this is going to be the radius. A lot of people will say radius. I'm going to flesh this out a little bit more. I'm going to say that this is the distance from the axis of rotation to the outer edge of the function. It would be better to say the outer edge of the region. This might seem like a little bit too much to say here. and I get that. I'm kind of course, I'm sort of redefining what a radius is. I mean, that really is what a radius is. But when you get into the washer method, I think this wording will be helpful. And then dx is going to be the width, or some people would say thickness, of the representative rectangle slash disk. And then, of course, r of y and dy, they mean the exact same thing, but they, of course, are in terms of x instead of y. And let's visit on that here for just a moment. Let's see here. Let's look at why these variables have to be what they are. So if I have some shape, and I'll use something similar to what we did earlier. I've got some shape like this, and of course this is my region right here. I'll erase that so I can draw in there. And if I am going to be rotating around the x-axis, in order for me to do that, using the disk or the washer method, my representative element, my representative rectangle, needs to be perpendicular to the axis of rotation. So if I were to draw that in, like I did before, then it would look something like this. So then this rectangle is y tall, right? From the x-axis up, it's y tall. But then this base length, you could think of that as the width or the thickness of the representative rectangle. As you guys know where we're headed with this, seeing the integrals from before, the width of these little rectangles is going to be approaching 0, so that we can fit an infinite number of them into my region. And so I need to have some flexibility there. And so some people would refer to this as, delta something, like a change or whatever. I'm going to refer to it as dx. That's standard procedure there. The reason why that's dx is because the distance from, let me get a different color here, the distance from right here to right here, this little red distance in there, that is literally an x distance. That's a left-right measurement, meaning that it's going to be a small little variance in x, and so we call it dx. Similarly, if we had a horizontal representative rectangle, that thickness would be measured on the y-axis, and so we would call it a dy thickness. So let's look at a couple of examples here to finish this off. Okay, so number one, find the volume of the solid formed by revolving the region bounded by the graphs of f of x equals cosine x and the x-axis on the interval from 0 to pi over 2 if that region is revolved around the y-axis. So I am going to draw a picture of this. I think that's extremely useful to try to visualize what's going on. So here's my y-axis, here is my x-axis, and then of course y is equal to cosine of x on the interval from 0 to pi over 2 looks something like this. 0 to pi over 2. So if we wanted to kind of formally get this sketched down here, that's not going to work. The region itself is going to be this region in here. There we go. So we're going to take that region right there. We're going to revolve that around the, oh, you know what? It's the y-axis. My fault. Let's go around this. So revolving around the y-axis. Okay, so if you remember from before, the representative rectangle has to be perpendicular to the axis of rotation. So I have to draw in a representative rectangle that looks something like that. That is perpendicular to the axis of rotation. Making this a dy thick rectangle, or dy wide. And it looks like it's kind of the height there, I get that, but it's still kind of a function of the thickness. The length here, of course, we'll be working with as well. It is a dy thick rectangle. So the significance of that is that everything that we put into our integrand, our integral, everything in the end is going to have to be in terms of y. So I can put, for sure, volume equals pi times the integral from somewhere to somewhere. We'll deal with that in just a second, of something or other squared, right? Pi r squared. But we know for sure it's going to be a dy. I guess I didn't talk a lot about why the formula is pi integral of r squared. Maybe I'll talk about that here in a second. Okay, so we need to start accumulating these little representative disks as they get rotated around the y-axis. So the first thing we need to tackle is the limits of integration. So my first representative rectangle is going to be, down here. And as I work my way up, start accumulating more and more of these, so on and so forth. There'll be some all the way up here, of course, up to the very top. I want to think about what that low value of accumulation is going to be. Of course, it's down here on the bottom. And so that has a y value of 0. Remember, everything, including the limits of integration, have to be in terms of y. Okay, and then I'm going to stop accumulating up here because that is where the region ends. So in terms of y, what is that value? Of course, cosine has a max height of 1, and so we're actually going to stop there at 1. So we're going to accumulate from 0 to 1, accumulating from bottom to top, like that. Okay, and then what goes inside here, of course, is r squared. That is the distance from the axis of rotation out to the outer edge of the region. So, of course, that would be something like this red distance right here. So I just had a little computer glitch, and I'm not sure where my video started and stopped, so I'm just going to do number 1 again. Maybe it's actually for the first time. We'll see. So if this is a repeat partially, I apologize. So this question says, find the volume of the region, or find the volume of the solid formed by revolving the region bounded by the graph of y equals cosine of x and the x-axis on 0 to pi over 2 when that region is revolved around the y-axis. So I'm going to sketch a graph of this real quick. On the interval 0 to pi over 2, cosine of x looks something like that. So this would be 0, this would be pi over 2. And then the region itself is in here. Again, trying to stay in the lines. It's kind of tough. There we go. So that region is rotated around the y-axis. So if you remember from before, whenever we're rotating around an axis, the representative rectangle has to be perpendicular to the axis of rotation. So that means that I have to draw in a little rectangle that looks something like that. So like we talked about before, the thickness of the rectangle is key. The thickness of the rectangle is really going to determine all the variables that we'll have in our integrand. So this thickness would be measured right over here, and the thickness, because it's measured on the y-axis, would be a dy thick representative rectangle. Of course, we are going to talk about this, length here. That's going to be important, but the thickness is dy, and that's very important because that sets up the rest of our variables. So I'm going to start off with this. Volume is equal to pi times the integral. We'll get the limits in there in a second. We're going to have a radius in there, of course, but I'm going to put dy over here. Okay, the next thing I'd like for us to handle is the limits of integration. I need to know where I'm going to start accumulating and where I'm going to stop. So my first little representative rectangle would be down here, and there'd be another one right here, and a bunch in the middle there, and more, and eventually I'd get up here to the top. So I need to stop and think about where I will start accumulating those, like what's the lowest value of accumulation, and what is the highest. That's where I'm going to stop. So the lowest level is down here, and of course, in terms of y, this is y equals 0. So my lower limit of integration is going to be 0. I'm going to accumulate from bottom to top, and so I'm going to stop right there. In terms of y, that value is y equals 1. So my limits of integration are going to be from 0 to 1. And then I have radius squared. So I'm going to just put blank parentheses squared. Let's talk about this now. Radius, of course, is the distance from the axis of rotation out to that outer edge. And so I'm going to try to draw this in for us. That would be a distance maybe from like right here out here, this orange distance that I'm drawing in. So from right here on the y-axis out here to the outer edge, out to the right, well, if you think about this in the most fundamental elementary sense, that literally is an x distance, right? It's from the y-axis measuring out to the right. So if I wanted to, I could throw an x in right there, and in a very elementary sense, that's correct. But the problem that I have is that all of my variables, including the limits of integration, have to be in terms of y, and that x obviously is not a y. So I need to replace the x with something that only has y's in it. And the way I'm going to do that is I'm going to use this y equals cosine of x. So I'm going to write y equals cosine of x, and I'm going to attempt to get the x all by itself so that I can substitute with that. So to do that, I'm going to do the inverse cosine of y, and that'll give me x. So I can come back up here and I can erase the x, and I can replace it with inverse cosine of y. Okay, and that would be the integrand that would lead to the answer. This would be something I would certainly not expect us to do without a calculator. The integrand is not something that our skill level allows us to get to. So I'll enter this in my calculator real quick. You can do the same, and we'll check back in a moment to see if we agree. And I'm coming up on my calculator with a value of 3.586. Okay, let's just take 1 second here. I want to make a little connection with you in regard to the volume of these types of shapes, the volume formula specifically. So the volume formula is volume equals pi integral from a to b r squared dx, or maybe dy. I want you to stop and think for a second. What do you see in these little boxed expressions? Pi r squared, right? That's the area formula for a circle. If I throw on this dy on the end, what I have here is pi r squared dy. And of course the integral is simply an infinite summation, it's going to make these disks super skinny, make an infinite number of them, and add them up. But here's the connection I want you to make. I think back in geometry we probably would have called these disks cylinders. So the volume formula for a cylinder is volume equals pi r squared h. Of course, you can see the similarities right away, right? The pi's, the r squareds, they all match up. But then the h and the dy, well, if you think about a disk or a cylinder, looks something like this. And of course, for our purposes, the axis of revolution would, come through like that. But in any case, the radius, I'll label this stuff for you. The radius would go from right here out to the edge. That's our radius. Pi is just pi. And then this out here, this would be the height. But the way that we're handling it is we're making that height, also known as our thickness, variable, right? We're going to make it so that the integral can squeeze it down to being super duper skinny. And so that is really a dy. And so these disks slash cylinders, like what you looked at in geometry, really truly are the same thing. So this would be the connection I'd want you to make, realizing that the formula here is simply just the integral of a bunch of super skinny cylinders. We call them disks. So please make that connection as best you can. Hopefully that'll help you remember these things better instead of just trying to memorize them. Okay, we got one more example to do. Let's take a look at number 2. All right, our final example here, number 2. The region that we're dealing with is bounded by f of x equals 2 minus x squared on the x-axis. Find the volume of the solid formed by revolving this region about the x-axis. So like we did before, I'm going to do a quick sketch. There's my y-axis, there is my x-axis, and then of course that region, that function, y equals 2 minus x squared, just a parabola. That parabola opens down. It's been moved up 2. So I'm going to stop right here at the x-axis because that's the other boundary for our region. So my region is going to be this right here. Let me just highlight this in as best I can. There we go. So that is my region that I'm revolving, and I'm revolving that around the x-axis. So like before, let's remember that using the disk method, or later on the washer method, the representative rectangle needs to be perpendicular to the axis of rotation. So here is my representative rectangle. So the representative rectangle, based on the way that we had to draw it, is dx thick. It's dx wide. So what that's going to do then is make everything within our integrand, the limits of integration of the integrand, everything is going to have to be in terms of x. So I'm going to set it up like this. Volume equals integral, oops, I forgot my pi. Pi times the integral from somewhere to somewhere, we'll deal with that in a second, of r squared, but the point is it's going to be dx. Okay, let's work on the limits of integration next. My other representative rectangles will be over here and here. Well, that one's not quite a rectangle, sorry about that. And so, yeah, this whole shape is going to be filled with these. As we rotate around, they'll make little discs. But the point is, if you notice when I was filling those in, I was filling those in a kind of a left to right, right to left manner. And so I'm going to look at it as accumulating from left to right. So over here on the left edge, that's where I'm going to start accumulating. On the right edge, that's where I'm going to stop. So the question becomes, what are those x values? Because everything has to be in terms of x here. The way that I'm going to figure this out is to use my original function, y equals 2 minus x squared. I'm going to set that equal to 0 because that'll give me my x-intercepts. And so if I do that, I get 2 is equal to x squared, and then plus or minus the square root of 2 is equal to x. That tells me this left edge is negative root 2, the right edge is positive root 2. So those will also be my limits of integration. I'll start accumulating at negative root 2, and I will stop at positive root 2. And then I've got my radius, last of all. The radius, of course, is the distance from the axis of rotation out to the outer edge of the function, or the outer edge of the region. So I'm going to start right here and travel out to right about there. So, quite literally, if I measure from the x-axis straight up, that is truly a y distance, right? That's really the definition of a y distance, from the x-axis measuring up or measuring down. That's a y distance. But of course, I can't have that in the end because this set of representative rectangles are all dx thick, so everything has to be in terms of x. So the way that I handle that is to recognize that, like before, y equals 2 minus x squared. So I can replace that y with 2 minus x squared, and that gives me the correct radius here. All these little details I'm going over might seem inconsequential, but they aren't. They're actually quite important. They will become more and more important as these problems become more complex. So once again, with the negative root 2 and the positive root 2, perhaps this might be one of those questions where the calculator was active, although this is one that you could do without a calculator. We'd want to FOIL out that integrand first. But I'll go ahead and use my calculator. You can do this by hand. You can do this on a calculator. Do what you need to do. Do what you need work with. And we'll check our answers here in just a second. So I got, with the calculator, using Math 9, 18.956. Okay, so that is it for the disk method. The next video will be about the washer method.